Uh, yeah. So yes, my name is Kayla Martin. I'm a PhD student here at Macquarie University under Ursula's supervision and Devika Math, who's not here. And I'm talking to you today about a paper we're currently working on called, there's a mechanism called the light common envelope. And we hope that this is going to be a new channel to explain the formation of both giant binaries. So for those of you who don't know what a post-giant binary is, typically, just to give you some background, the primary star is post-giant because it's just left the giant phase, so either the RGB or the AGB branch. It's relatively dense core, small, and it has a very thin envelope of around 0.02 solar masses because it's been stripped on the thermal pulse phase. And the companion star is a star like our sun of around 1 solar mass. And we also see observationally these large circumbinary disks around the systems, which are very extended out to large radii, and they're extremely stable and very, very low mass, 0.01 solar masses. And another fascinating thing about this particular class of binaries is their eccentricity and their separations. And so typically what we would expect for systems of this mass are they go through what we call the common envelope phase, whether you're familiar with that or not. Usually the primary star expands to a giant, and that's when it becomes, that's when it engulfs its companion. Normally we would expect this to happen, and then you would see a very close or tight orbit that is circularized. But clearly what we see is not that. Very, very spread out in the parameter space. So that got people thinking, did we potentially avoid an interaction? Was there alternative interactions? We don't know, but what we're trying to work on is explaining that. And if you look at the tidal capture radius of the primary, whether it's an RGB star, which is on the right, or an AGB star on the left, on the right, we can see that all of the current orbits observed today for these systems fall well within the tidal capture radius. So this tells us that they have to have interacted when the primary was a giant. And another interesting thing, which we hope to kind of start explaining, is that these systems also show a lack of planetary nebulae, which is another common product of the classic common envelope phase. We tried to explain this, at least in part, in our previous paper last year, where there's a mechanism on the post-giant branch where essentially the big disk is sharing mass through accretion streams onto the stars, and that changes surface chemistry and things we see observationally. So we tried to see if whether this mechanism could extend the post-giant phase long enough to potentially give circumstellar material that had been lost by the primary time to essentially move far away from the star before it gets hot enough to ionize. But despite this being a sufficient mechanism to extend the post-giant phase, it's not long enough to avoid forming a planetary nebula. So our thinking is we need a weaker interaction regime to reproduce these systems. Ideally, this weaker interaction scheme will slow the rapid in-spiral we see for typical CE. We also want to avoid the envelope engulfment of the companion in the primary. Ideally, we want to preserve high eccentricities and wide orbital separations. And as a byproduct, hopefully we can also siphon the envelope mass that has come off of the primary and store it somewhere so that it can't be ionized to form a planetary nebula, to explain the absence of these. So we are introducing a mechanism which we call the light common envelope. Essentially, it's the diet version of a regular common envelope. We have a very low envelope mass, so you have less binding energy available. We don't see a rapid in-spiral. We do not fully immerse the companion in the primary envelope. We see self-regulated mass transfer, and we also see angular momentum loss through strong mass loss out the back of the primary and companion through L2 and L3. And what we predict is that this will cause wide separations, non-zero eccentricities, formation of a circumbinary disk in the form of storing material in the circumbinary environment, and we ideally will see no heat. So to model the LCE, the light common envelope, we start by making our giant primary star in Mesa. So we've taken this from our first paper from last year. The star has a mass of 0.8 solar masses, And we take it at the lowest possible envelope mass for MESA, which is around 0.25 solar masses. And this is much lower than what's typically used for regular common envelope simulations. We then map and stabilize this star in Phantom. And we use two different resolutions to hopefully get convergence. And the main thing we care about is mapping the density profile, but we do also care about the thermodynamic properties. We're also currently using ideal gas, but we're in the middle of trying to get Mesa equation of state to stabilize as well, but that has some troubles. I just wanted to point out as well that the stability of our star, it was very difficult to get. We spent a lot of time testing this and a lot of different trials. These are the best of the bunch. Please ask me about that later if you're interested. But the next step we did was we added a sync particle companion using Phantom Model, whether you're or not you're familiar. We varied the mass of the companion, and we also, this then varies the ratio of masses in the system. We used an accretion radius as well of either 0 or 3R sum, which is roughly 3 times the size of the companion, just to kind of isolate the effect of what a low envelope mass would actually have on the CE versus LCE regime. We also set the initial separation of the system to be the Roche-Loeb overflow distance. So essentially, we know that the primary is going to immediately start sharing mass with the companion. And we also varied the eccentricity. So 0, again, to isolate the effect of a low envelope mass, but 0.4 because it's the most typical range in post-giant binaries observed today. There we go. So what we do find, which was great news, is we do see a long, steady in spiral that actually results in quite wide final separations. So we get from between 100 to 450 R sum. So roughly in the larger case, we started at 900 R sum. So it's a 50% decrease in orbital separation. In either case, the 100 is our low Q ratio, which is still around 10 times larger than what we expect for canonical CE, which is around an orbit of a few tens of days. Tens of R, sorry. We also do find, it's a preliminary result, non-zero eccentricities of 4. But again, we'd like to see what happens when we try our Mesa equation of state stabilization. Also, we wanted to test whether the companion is engulfed in the primary envelope. So again, preliminary results, but what we find is for the higher Q ratios that we've used, we do see that if you look at the red line, which is the orbital separation, in the high Q case, it's clearly much larger than the primary radius or the outer envelope of the star at all times. So we completely avoid the immersion of the companion. And this is the system that ends up with the 450 R sun separation. In the medium mass range, still high, we do see there's a tiny almost engulfment, but more of a brazing effect. And in the low Q, which is arguably the hardest to avoid a common envelope in, we do see there's envelope immersion. But interestingly, and what we'll look more into, is that even though it's engulfed for 15 years in the primary, it still ends up with 100 R sun separation, which, like I said, is around 10 times larger than what we would expect from typical CE. And so what we're thinking is that essentially it undergoes a weakened common envelope. And this is also truncated by a very low envelope mass. So then, if it's not engulfment of the companion, what is driving the in spiral at all? We say in spiral because it's weakened. It's these large L2 and L3 tails where mass is being lost and it's losing angular momentum from the system, rather than the typical dynamical drag that we see from envelope and companion immersion. And essentially, for all of our Q ratios, all of our simulations, we find that the L2 and L3 outflows are much stronger than the Roche-Loeb overflow. And again, preliminary work, but we find a gamma of around 6, which essentially is just telling us that even though angular momentum loss is very efficient with mass loss, it does truncate early, again, because of the available envelope mass. And this is what results in our final separations being quite wide. And the envelope, essentially, pretty much all of it is stripped, 80% in the lowest case, 99% in the highest case. The companion ends up accreting very little of this mass. And that's interesting because we typically would have a big accretion disk form around the companion. But essentially it goes in, it swings around the companion, and it's lost out the back of the companion. But the mass is not lost from the system, it still remains bound in the circobinary reservoir. So as a summary, we are successful in producing wide eccentric orbits, which is more consistent with the post-giant binaries that we see today. There is some work to do, of course. We do strip the envelope, which is great, and it goes out in these giant spiral tails. So we do retain the envelope in the circumbinary reservoir rather than ejected. And this then provides a natural pathway to suppress planetary nebulae formation because we have captured and retained the envelope rather than it being lost to the environment to be ionized later by the star. So promising preliminary results, but there's obviously some work to do, including getting our Mesa equation to stabilize. But yeah, thanks for listening. Questions for Kayla?
Ali. I think we don't need the microphone because his microphone's on the ceiling.
It works quite well.
Yeah. If anybody can't hear or would like us to use the microphone, just let us know.
I'll try to be loud.
Pretty pictures on.
Yeah. Thanks, Ali.
Thanks for the nice talk. I just had a simple question. How do you define the primary's radius when it's that extended?
So our primary star is always overflowing its Roche slope. So it's got a filling factor of pretty much exactly 1. So right now we're taking the surface of the envelope to be the Roche slope radius. It's in all cases. We did check that first.
Okay.
But yeah, you can check what is bound to the core of the primary, but it would take a little bit. So for now, again, like I said,
Can you use like an L3 radius if it's
complicated because we've also got flows.
Yeah.
So some mass, if it was smaller than its Roche flow, would be included in the flows. So again, we're using it essentially as an approximation, but I would say it's a fair approximation in this particular case.
About the great talk. I actually love the way the Q was represented there because you can see the morphology evolution. But my question is about the Mesa star. Did you use any special kind of parameters when you create the star in Mesa, or you use the default values to this?
So the Mesa star was created for last year's paper, which was modeling post-giant stars. And so we focused on essentially we wanted to make sure the envelope mass was 0.02 solar masses to match observations today. And so when we set our star up, we evolved it from the main sequence up the giant branch, and then we stripped the envelope using a high negative accretion rate in Mesa. We can't do stripping directly. And this then allowed us to strip the envelope down. We did set composition for the envelope gas because as we were talking about depletion in the paper, but yeah, other than that, mainly just focusing on the masses and the envelope mass, and also the radius of the star being reasonable at the time we took it off the Mesa. Next question. Yeah.
How many? Your primary star, do you have a sync particle instead of a core, or do
yes. we add a 0.55 solar mass particle because that is the core mass of post-giant stars today, and that is the mass of the star when we took it off of Mesa. And we add 800,000 particles as the envelope around it.
So it corresponds to the actual physical core?
Yeah, exactly. Okay. But we care mostly about, our star is 330 our sun, and the core is 0.02.
Yeah, but I'm saying this because I'm guessing part of your equation of state problem comes from the layers around the core.
It's interestingly, there's been a lot of questions surrounding this, but interestingly, the problem seems to be closer to the surface. There seems to be an ionization zone.
Of course, yeah.
It's causing lots of particles to fall in through convection. But we're in the middle of figuring out whether that's actually going to stop us from moving forward or not. But
if you ever solve that problem, let me know. Because I haven't been able.
Yeah, I guess what we're trying to do is more so just minimize the effects. So we're working with Mike Lau to try to use essentially a constant entropy in the envelope before we put it in. So instead of a Mesa profile, we would recreate the density profile of the star.
Yeah, that's why I did as well. It's Mike's method too.
Yeah, exactly. But these are all the tests we're trying to work on. Hopefully we
That
can
means
solve it.
that means you get no convection, and that's a shame.
Yeah, it's a
Well, the
trade.
problem is it does want to.
Yeah.
Yeah. Do you want to come and set up? While Antoine does that, time for one quick final question. Quick question.
Hi, quick one. I mean, it's not my field, but I know Ilya talks a bit about when you do binary interaction, assuming rush lobe overflow, people tend to assume isotropic re-emission, that the angular momentum just goes like, and then gets re-emitted as like a jet